This is joint work with Liang-Ting and Tzu-Chi, and they're here as well. Right, so what our work is about, it's about libraries for dependently typed programming, and especially in Agda, because that's our favorite programming language. So usually we have lists in our library, and we know that a list is a kind of container that maybe has some elements of some type A. So the library can also provide this list any data type for us to be able to point to a particular element of a list and say that it satisfies a particular predicate P. So to be specific, we use the here constructor to point to the head of a list and say that it satisfies P, or we use the there constructor to say that the element is somewhere in the tail. And usually in the library, we have some associated operations as well. For example, this lookup function that basically extracts the element being pointed to, and also the proof that it satisfies P. Right, so what's interesting here is that this any construction is not specific to lists. Whenever we have a container-like data type, we kind of expect that there's a corresponding any data type and the lookup function. And for example, the library may also have this data type of binary trees that has elements stored in their leaves. Then we would kind of expect that the library should also provide this tree any data type and a lookup function. Okay, so for general purpose data types, such as list and tree, we can kind of expect that, well, it's okay to just put everything in the library, right? We don't have to do anything special. But we often write our own special purpose data types. And they can get pretty complex, especially in a dependently typed setting. So we really can't hope to find them in a library. A typical example would be an embedded DSL. So here, starting from an untyped lambda calculus, we may want to extend it to some mysterious language, and we put in well-scoped variables. So we need data type indices now. We also need some additional constructs such as let expressions and maybe a mysterious construct that's specific to this language. And we may use various data type features such as data type parameters and universe-polymorphism. So this is data type that we can't hope to find in a library, but we still want library support. For example, here we might want to prove some theorem about this mysterious element. So we would want the library to give us, basically from this definition, we should be able to get this missed any data type and its lookup function. We want library to give us this. So what the library should provide is a generic any construction that works for all container-like data types. And ideally, the definitions that give us should be something like this: a native definition, a definition that looks like what you would have written by hand. Well, why do we want native definitions? It's because when we go on with our development, so here we're actually proving that some theorem that says for any term T, if it is well typed, then any mysterious element in it is nice in some way. So the first thing we do is probably try to k-split on the missed any argument, so listing all the constructors. And also when we try to find the goal type of a whole, the definition lookup missed any would show up nicely and also compute nicely. So that's what we want. We want the libraries to give us generic constructions for deriving native definitions from our own data types. So how do we develop such libraries? Well, since we want native data types and functions, in Agda we can do that using Elaborator reflection. So the reflection API provides a set of data types representing Agda constructs so that we can manipulate Agda syntax within Agda. So here's an example. This is the data type representing Agda terms. We use the var constructor to represent a variable in the form of a de Bruijn index, and which can be followed by a list of arguments. We can also represent lambda expressions, literals, and so on, and also type expressions. Here, the pi constructor represents a dependent function type, and its two arguments are the domain and codomain. So sometimes the API writes type instead of term to informally say that actually here what we want is a type expression. And perhaps more importantly, the reflection API also provides a type checking monad TC and a set of primitive TC computations. And so these primitives, we use these primitives to write metaprograms or macros in the form of TC computations. And and then these metaprograms can be run during type checking. So for example, we can use the first two primitives, declare def and define fun, to declare the type of a function and give the definition of the function. And my co-authors have spent quite some time hacking Agda to allow declaring data types and defining data types as well. And it's now in the development version of Agda, so you can try it out. And what's special about Elaborator reflection is that it provides some very powerful primitives for that expose some of the functionalities of the Elaborator. So for example, here we have unify. It unifies two terms and also solving some meta variables appearing in those terms. And we also have this normalized primitive that normalizes term. This turns out to be very useful, and we will see later. Okay, so that sounds good, but actually we don't like it because the representations are very imprecisely typed, and as an Agda programmer, we hate that. So here the example is something like we're trying to write a type, a pi type, but we may accidentally supply a wrong kind of expression, and we may supply an out-of-bounds de Bruijn index. And this makes writing generic constructions using purely Elaborator reflection very difficult and very error-prone. But there is a solution to this problem, and that is Datatype-Generic programming. I'm not going into the details, but in Datatype-Generic programming, we usually use very precisely typed representations to write our generic constructions and thereby proving them correct. So here, data D, short for data type descriptions, is our representation of data types. And inside data D, we use this con D data type to represent constructor types. So let's go back to the example. So suppose I use con D to write a function type that has at least one argument. Then the argument type, we would use the sigma constructor to do that. And because of the type of sigma, we definitely have to give a legitimate type as the argument type. And later, when we need to refer to the argument, we use an ordinary variable of the right type. So everything is under control by the type checker, which is good. And actually, in our representation, we also did something about universe level correctness. So we have a lot of universe levels appearing in our data type and need to satisfy those constraints. And we can actually require those constraints to be satisfied because Agda's universe level are internalized. So we can actually reason about them in Agda. So that's a plus for Agda. Okay, that also looks nice, but still we don't like it. It's because traditionally, and especially in Agda, we would use this mu data type to convert data D into actual data types we program with. And it looks ugly. I hope no one is parsing it. So don't worry about it. But I think what I want to draw your attention to is that it's actually very inconvenient to use. So there's a generic constructor con here that basically encodes all the constructors of your data type. And now if you try to k-split on this, it gives you just con rather than all the constructors. So language support is gone, and you're left with this mess. Okay, so what do we do? Actually, it's kind of obvious. We just continue to use data-type generic programming techniques to write our generic constructions, but at the end, we don't use the mere data type. We use Elaborator reflection to manufacture native data types and functions. So that's kind of simple. That's the basic idea. But if we want to give it go into some more detail, then suppose that in my library there are already two generic constructions, NED and lookup any, and I want to instantiate the constructions for my own data type MIST. Then we need to write some interfacing code. So first of all, we need to use a macro, genDataD, to generate a data description of MIST. And that's the input to NED. But NED requires some more information, actually. It needs to know that MIST-D somehow corresponds to MIST, so that it can actually refer to MIST and its constructors in its construction. And this connection is also generated by a macro, so it's not a problem. And specifically for NED, we need one more piece of information. That is, we need to tell NED where in MIST we want to point to. That's the red circle we saw back there. And to specify that, here we're giving a proof that MIST-D is actually a simple container. You can find the definition in the paper. So now we can invoke NED. That's the description of the MIST-NE data type, which we can turn into an actual data type, a native data type, by another macro defined by DataD. Usually we can stop here, but if you want to continue to do more instantiations, then we should establish connection here as well, so that, for example, lookup any can be instantiated for MIST-NE. Right. So actually, I want to talk about this instantiation of lookup any as well, because it's kind of interesting. Lookup any computes an F algebra, and that's turned into a native fold function by the macro define fold. And inside the macro, what we do is just write basically a definition like this. Here, fold NT and fold base are generic definitions of the type and body of the fold function. And the idea is to use normalize to just expand the definition. So, and get a clean definition for lookup MIST-NE. But there's a catch, because fold base doesn't actually expand unless you instantiate, you replace I with some actual constructors. So we have to use Elaborator reflection to do some kind of case splitting ourselves and to generate this kind of definition. It's actually not that hard. You can see that it's actually very mechanical, so it's manageable. And finally, we just normalize the right-hand sides. And that gives you the clean definition. So I think one of the questions now would be like, can we use the generic library now? The answer is, of course, no, not yet. Why is that? Of course, we have experimented with some generic constructions in our paper, like the standard fold operator and its fusion theorem, a bit of algebraic ornamentation, and the all and any predicates for simple containers. And later, we also experimented with some syntax generic operations, such as renaming and substitution, which we talked about at Tidy a couple of days ago. But there aren't many, and I think we need many generic constructions to be able to call them a library. So we need more. And also we need to extend and refine our framework. We want to support more forms of data types and functions. we want to reduce the effort of writing the interface code, because that's a lot actually. And also we want to spend more time with the macros, because it's actually difficult to get them right, because we simply don't have a very good way to deal with macro correctness at the moment. And finally, everything is kind of slow right now, so somewhere has to be done. Yeah, it's a lot of work, and of course we'd appreciate any help we can get, but hopefully eventually we'll be able to get to a generic library that the practical Agda programmer will be happy to use. Okay, thank you very much.